in the context of asteroid rotation's evolution. Those collisions, those catastrophic or smaller collisions, are usually thought of that they do not play a very important role, but we would like to investigate on this more thoroughly. They act upon asteroids almost permanently because of the power law distribution of projectile sizes, which means that their cumulative effects may actually be important. The main motivation for this research is that we are trying to investigate the origin of so-called tumbling asteroids, which are the asteroids that are freely precessing. They are not in this principal axis rotation state as the majority of them. In our previous research, we showed that some catastrophic collisions may actually be responsible for the excitation of rotation, and I will briefly comment on this. This graph shows the spin rates and also the periods of the asteroids over here versus the diameter in kilometer, and it's only part of this graph actually. And these are observations. The red diamonds are those tumblers, and the green squares are those principal axis rotators. And what is highlighted on this graph are only those bodies that we are quite sure what their period and rotation state is. And you can see that for the slower part of the rotations, let's say periods of more than 24 hours, there are two distinct groups of the bodies which are almost the same. So this dichotomy of slow rotators is quite remarkable, and any model should be able to explain this. Now, what our model looks like. The projectile collides with a target asteroid, which is represented by a triaxial ellipsoid rotating in the basic state, and forms an impact crater on its surface. The dimensions of the craters are calculated according to scaling laws by Hossetto 1993 and 2003, and there is a linear and angular momentum exchange between those two bodies. Part of the momentum and angular momentum is carried away by ejecta, which we include in our model by calculating the angular momentum transfer efficiency based on the laboratory experiments of Yanagisawa et al. 1996 and Yanagisawa and Segawa 2000. Then we calculate the inertia tensor of the target asteroid and produce its light curve. And we, by the classical photometric method, we judge whether the asteroid is rotating in a principal axis rotation or it is tumbling. We also compare the specific impact energy of the collision to the shattering threshold energy of the target, so that we are sure that the collision is actually subcatastrophic. Now, these are the results that we obtained. This is a graph of specific impact energy versus target size. Both the axes are logarithmic, and all those points are the results of our simulations. The red dots are those bodies that were not excited. Their rotation wasn't excited enough so that we could observe it in their light curves. The green dots are those bodies that were excited enough so that we could observe it, and the green crosses are those bodies that were shattered or dispersed by the collision. So we can see that there's a group of bodies, those green dots, that actually were excited by the subcatastrophic collisions and were not dispersed or destroyed by the collision. Now, we proceed with this research, and we ask those main questions. Whether collisions are sufficient alone to explain the tumbling, how probable is to observe tumbling asteroids with rotation excited by collisions, and whether collisions are able to explain the observed characteristics of tumbling asteroids, mainly the dichotomy of slow rotators. So the main goal now in our model is to build a synthetic population of asteroids colliding with small projectiles, and compare it with the observed sample of slow rotators. Basically, it means that we only describe the period of asteroid lifetime between large collisions, which for a kilometer-sized asteroid in the inner main belt is around several hundred million years. The targets and projectile sizes obey the parallel incremental distribution as described in Begrade 2005. We calculate with an isotropic geometry of collisions because those bodies have inclination span of some 35 or maybe even more degrees, and the rotational axis may be randomly arranged for those bodies. Although it is also possible that small targets, such as several kilometers in diameter, may be trapped in the so-called Slaven state. But Begrade et al. 2003 also showed that it is possible that smaller bodies may actually escape this resonance state. So we think that the isotropic geometry is quite okay for now. This is the distribution of targets, rotation, or spin rate of those target asteroid. It is actually observed distribution of spin rates for main belt and Mars crossing small bodies in the size range between 3 and 15 kilometers, as described by Graves 2008. And this graph is updated last year, so it's quite new data. Now, what are the preliminary results or main features of the model that we observe? We see the increasing elongation of non-spherical asteroids caused by consecutive collisions, which basically is an erosion or collisional erosion of the body. And in our model, it was indicated by Brownian axial ratio of dynamically equivalent ellipsoid, which we calculate from the target's inertia tensor. We estimated the time scale of this process to be on the order of tens to about 100 million years for a kilometer-sized asteroid in the inner main belt. And the explanation is that the crater or the cratering collisions erode all dimensions of the body by the same amount on the average, which means that the smaller dimensions decrease relatively quicker than the larger one. And it was briefly described by Heynch in 1990. And this graph shows what we observed. It's a graph of axial ratios of the target asteroid versus the number of collisions. And you can see that the initial axial ratio of 1.4 to 1.2 to 1 grows for all the axes. Now, another result is that, or another feature is that collisions tend to change the rotation of the target, but there is a difference between large projectiles and the smaller ones. In decimeters or meter size range of the projectiles for a kilometer size target, we observe the increasing spin rate on average, and also they cause the observable excitation of rotation, while the smaller projectiles in millimeters or centimeter size range tend to decrease the spin rate in about 60% of our rounds. This is consistent with Harris' 1979 theoretical model of asteroid rotation evolutions, and we actually observe this when we are looking for a lower cutoff size of projectile sizes that we need to include in our model, because we can't simply calculate all the projectiles down to, say, micrometer sizes because of the computational burden. So we are looking for some analytical approximation to include in our model so that we wouldn't have to calculate so many collisions. Now, these results are shown in these graphs. This is for the meter-sized projectiles. It's the graph of post-collisional angular momentum divided by the initial angular momentum, so it's just normalized, versus the number of collisions. You can see that usually in those sample simulations we observe the increase of the spin, and when we add some small projectiles, like centimeter sized, we observe the spin down, as well as in this situation when we added also some millimeter sized projectiles. Also the number of collisions grows very quickly, so That's why we are actually looking for some analytical approximation. Now, there is one work ahead actually, besides this analytical approximation that I've already mentioned. We have to include the damping of the excited rotation into our models. There are two models in the literature that I know of. It's Breiter et al. 2012 and Sharma et al. 2005. We will calculate collision probabilities, then run the simulations to build this synthetic population of asteroids, of slowly rotating asteroids. And then we have to also simulate the photometric observation biases so that we could observe actually this synthetic population to the observed one. Okay, that's it. Thank you.
We have plenty of time for questions. Yes, sir.
Just a small comment. Following the theory of Harris, which you have mentioned, there was another paper with theory of tumbling asteroids. It was much more sophisticated and elaborated. It was a theory by Rimsky. Yeah. Maybe it would be worthwhile to give a look at it. Okay. I didn't see that you are aware of that paper.
I've read it, I think.
It's
it's also concluded by Sharma. It's reviewed by Sharma. So it's also very useful to read.
Yeah,
Thank you.
sorry. Actually, there is some kind of discussion about the characteristic times of the tumbling. And a Rimsky model provided quite another estimation of the tumbling. So it's very different from Sharma and Breiter model.
Qualitatively, it's basically the same.
Yeah.
They have the same equations, but the scaling factor is different, so the time scales are a little bit different. But it's actually not such a big difference, I think.
100 factor.
I don't think so. But I will check it. Okay.
About the time scales of the process, you got one kilometer asteroid.
Yes.
What if the object is larger, maybe 10 kilometers? Is the process
Okay.
faster, or what I expect is slower probably?
The time scale actually grows with the size, but very slowly. I've done some dimensional analysis, and it's like proportional to R to 1.2 or something like that.
And your object is essentially compact, or it can be a rubber collide?
Well, it's compact. It's homogeneous.
Yeah.
Yeah.
Okay.
I can't really change it. I can do it with using another scaling clause for a porous body, but it's not perfect, I think.
You might want to check the paper that we published with Francesco Marzari and Dan Shears and Nicholas in 2011, where we analyzed the effect of collisions for the explanation of the excess of slow rotator in combination with the York effect.
Okay.
It actually touches very similar subjects, and we show that collisions with small projectile that carry an amount of angular momentum comparable to the angular momentum of a body when it's very slowly rotating can alter this. We can keep the spin rate in a kind of random walk for a while and then restart the acceleration of the asteroid.
Okay.
2011.
Peter?
I'd like to comment on the model of the damping. I'm afraid that most of the models are not self-consistent in the sense that they essentially have a free parameter, that's the dissipation rate. Do you know about models which are more involved in include internal mechanics to constrain the dissipation rate? Because otherwise it's only a free parameter. You have to tune and calibrate the observations.
Right. I think that those papers by Sharma, Rimsky, and those they basically were theoretical papers. So they dealt with detailed mechanics in some simplified manner. So the Sharma paper, if I recall it, is for 3x11 ellipsoid. A Rimsky paper was like some more regular shape, I think. But there was a detailed mechanics of the energy dissipation.
But still the coefficient.
I think the coefficient is often material constant. So,
Well,
respect to your context, because you would like to fit the number of tumblers with respect to the number of PCA rotators.
Yeah, I see.
And then you have to either have to tune this the same parameter, or you would like to constrain it using a completely another approach.
I see.
Did I understand correctly that according to your model, the low energy collisions tend to erode the object more quickly along the shorter axis and over longer time scales along the long axis?
Yes.
Because this would be important to explain the fact that there are so many, several examples of small objects that are below beta.
We just had the same question. It reminded me also of Itokawa.
Well, it's possible, but it also depends on the time scale actually, because we discussed this with Alan Harris, and he just wrote me that basically this is erosional effect, which is known like 100 years, or maybe even more. So I only don't know whether someone already published this in the context of asteroids. I'm not aware of any such papers.
One should look, now that we've had a more shaped model, one should look whether we can find among small asteroids other examples of but I think also Andrea had the question.
No, that's related to this. You already started with it elongated, so it is already elongated at the beginning.
That's right.
What if we start with a sphere?
Well, we also tried different shapes with
It
smaller
always
pixel
works.
ratios, and it also works, but it's just I don't know what to say. Well, it's not so prominent.